Hi, my name is Samir Sridhar, and I'm joined by my partners Chris, EK, and Kiono. The four of us make up Team 2 of ME 4056 Section LO5's Refrigeration Lab Block. In this lab, the company Machine Chillers has developed a cooling system based on a vortex tube that uses air as the working fluid for safety purposes. We in Burdell Inc. are tasked with modeling the system and its capabilities. The first week's focus is analyzing the system's steady state response, while the second week involves characterizing the transient response of the system. The diagram in front of you describes the experimental setup of the refrigeration lab block. Compressed air starts in station 1 and flows downward into a heat exchanger, ensuring that the air is cooled to ambient temperature if it wasn't already. After passing through the accumulator tank and getting cleared of any rapid pressure variation, the air moves to station 3, where its temperature is ambient and pressure stable. Then the air moves to the vortex tube, which splits the incoming airflow into a cold output, station 4C, and a hot output, station 4H. The higher temperature, ambient pressure air leaves station 4H and vents to the atmosphere, while the air from 4C feeds into an aluminum block with a heat exchanger flow path, thereby cooling the block as the cool air flows through it. Finally, station 5 measures the output air from the aluminum block immediately before it vents into the atmosphere. With regards to methods of data collection and visualization, LabVIEW is used to record pressure, temperature, and fluid flow of the air. Excel was used to store and display the completed data sets, and MATLAB was used to parse through, manipulate, and convert the collected data into understandable, palatable graphs. Here's a quick overview of the deliverables from week 1 that we'll discuss later on in today's presentation. Here, this slide succinctly summarizes the offset values calculated at 0 psi to accurately model, represent, and understand the subsequent data at different voltage.
Hello, I am Yunkwang Lee. Let me talk about the analysis. This slide contains several assumed constants what we use to analyze. This is the data of P3 versus voltage gathered from first experimental lab. There are two plots. One is quadratic fit data and the other is linear fit data. P3 has positive relationship generally between voltage. Quadratic fit is better than linear fit to describe pattern of P3, since the increasing gap of voltage at 2.5 is smaller than starting point, and the quadratic fit pattern is also appropriate to identify the pattern that P3 becomes stable at steady state. Then let me talk about the characteristic of vortex tube at steady state. Temperature of hot air and cold air, both data do not linear fit. Quadratic fit is more appropriate for describing pattern of temperature. Temperature of hot air increases as pressure increases, and temperature of cold air decreases as pressure increases. Also, difference between temperature of hot air and cold air becomes bigger, and magnitude of rising of temperature of hot air is bigger than cold air. From this plot, we can note the fact that heat exchanger cannot dissipate all of heat. This slide shows the data mass flow of cold air and hot air. Both of mass flow increase as the pressure increase, but only mass flow of cold air increases linearly and mass flow of hot air does not. Magnitude of rising of mass flow of cold air is bigger than hot air. In previous slide, magnitude of changing temperature of hot air bigger than cold air, so magnitude of Q from hot air and cold air would be close.
For the next part of the lab, we conducted a steady state analysis on the refrigerated load. In order to do this, we first calculated the theoretical insulation thermal resistance. This depended on measurements of both the block and the styrofoam insulation. Values of insulation area, thickness, and thermal conductivity were used to calculate a theoretical R insulation of 17.1768 Kelvin seconds per joule, using the formula pictured here. This value of R insulation will be used to calculate a theoretical Q dot ambient for varying voltages in the following slides, as well as in week 2 of the lab. The experimental insulation thermal resistance, RINs, and insulation thermal conductivity, KINs, can be seen in the table below, and the behavior in relation to voltage is visualized in the plots. In general, the experimental R insulation values are much smaller than the theoretical value of 17.1768. We can expect the experimental value to be less than theoretical because the material has imperfections in it, such as holes and cracks. The K insulation values are not consistent between tests. However, there may be a more distinct linear relationship if the outlier data is withheld from the linear fit calculation. The 1 volt data is an outlier potentially caused by an experimental error in data collection. Perhaps there was turbulence or other effects that affected the sensor readings, or a human error such as not waiting long enough for steady state to be reached to record the data. Here's a comparison of the theoretical and experimental heat transfer rate due to ambient heating, Q dot ambient, a steady state for varying input voltages. It can be seen that in general, the experimental Q dot ambient is greater than the theoretical value. This is due to the inverse relationship between Q dot ambient and R insulation, pictured in the formula here. As previously discussed, the smaller experimental R insulation value causes the experimental Q dot ambient to be greater than the theoretical value.
My name is Chris Caveney. I'm going to be covering the conclusions on our team's results from week 1. So, as was listed in previous slides, there were some discrepancies between our theoretical and experimental R insulation values and our theoretical and experimental Q ambient values of steady state. And as shown before, the theoretical value for R insulation was around 17, while the experimental values were all significantly lower. This high discrepancy can be explained by multiple sources of error relating to the styrofoam block's insulation. First off, our calculation of the block's theoretical value likely suffers from some error in our estimations of the block's area and thickness, so we're told to assume the block was uniform in shape and size when taking measurements. An additional source of error could be that the styrofoam block has been through heavy use, so it has cracks, holes, and small chunks missing, which would certainly cause our experimental values for R insulation to be far different than a perfect theoretical block. These arrows then have a domino effect on the Q ambient value because Q ambient uses the R insulation value in an inverse relationship that is shown on the formula here. This means that as R insulation goes down, Q ambient goes up and vice versa. So, due to the error from estimating the theoretical block, as well as the error from the experimental block having so many physical flaws, the experimental R insulation value was much lower than its theoretical value, and thus the experimental Q ambient value was much higher than its theoretical value. Our team believes that discrepancies between experimental and theoretical values could be lowered if the lab is conducted with an insulation block of higher quality. If the styrofoam block was more uniform in shape and didn't have any physical deformities, the team would expect our insulation and Q ambient values to align more closely to the theoretical values. So, looking ahead to week 2, the team will be conducting trials on transient data rather than steady state data. After the offset values are calculated at 0 voltage, trials will be run to obtain data at 40 and 80 psi, where we will use the P3 versus V quadratic fit from week 1 in order to determine voltages. The team will use this data to obtain experimental values of Q ambient, Q load, and Q air using the formula below. Lastly, the discrepancies between the experimental and theoretical values will be measured, and uncertainty will be calculated as new sources of error will be determined. And lastly, for our references, the team used the refrigeration equation sheet as well as the refrigeration lab guidance shown here. Thank you.